Hi guys, how are we doing? So first I'd like to start this off by asking a question. Who's ever been driving in Boston and say big dig in the tunnels and got lost because their GPS didn't work? Alright, this is a similar situation that submarines encounter while being underwater and being unable to access GPS to measure their acceleration, velocity, or position. Our group is the Underwater Accelerometer Sensor Optimization Group. My name is Mark Eckerson. This is Corey Tupin and Gregory Bridge. As Professor mentioned, our sponsor is BTech Acoustics, a local transducer and hydrophone company based in Fall River. And our advisor was Dr. David Brown, and our client was Dr. Corey Basham. So to start this off, submarines use arrays of sensors located on the submarine to measure the velocity, acceleration, and position. Some of these sensors are accelerometers. Accelerometers use the piezoelectric effect to measure, to transform the mechanical inertial energy to electrical energy, which can then be used to determine the acceleration of the device. For our project, we were very much so working with the very detailed portions of design that engineers often encounter in the optimization process. So for our accelerometer here, we have an outer syntactic foam housing that created neutral buoyancy for the accelerometer sensor. This was required because the accelerometer is being used on a submarine. And then we also have the inner housing of the accelerometer made of aluminum that protects the sensor internals of the accelerometer. We were given the task of optimizing the design of the accelerometer housing to increase the factor of safety and to reduce the cost. We were given the constraint that the accelerometer had to maintain its frequency bandwidth operation and maintain or increase the sensitivity. So for this project, one of the things that we worked on to reduce the cost of the accelerometer was the syntactic foam. So what we did was we worked on designing a method of encasing the accelerometer in syntactic foam and moving away from BTech's original machining process that they used previously, which was buying large blocks of syntactic foam that was very expensive and machining them to fit over the accelerometer. To do this, we had to develop a method of creating our own syntactic foam material. We did a lot of research and testing in this, and we're going to explain that later on in our slides. We also generated a manufacturing plan in order to produce about 10,000 accelerometers with under $200 or less per each accelerometer. So I worked on the testing and development of the syntactic foam and also compiled the testing and evaluation procedures for evaluating the accelerometer using COMSOL multiphysics for theoretical calculations. Greg Bridge worked on the assembly and testing of the accelerometer, and Corey Tupin worked on the machining of the accelerometer components and also helped Greg with the testing of the accelerometer. So for our final design selection, we wanted to increase the factor of safety while reducing the cost. So like I said, originally BTech was using a machined syntactic foam outer housing with this flat plate design to protect the sensor elements from the outside environment. We ended up moving to an elliptical cap design to increase the strength-to-weight ratio and reduce the mass of the internal sensor so that we could increase our foam density to reduce the water absorption of the foam that we were experiencing during testing. We also, like I said, we moved to a pourable syntactic foam outer housing, which greatly reduced the cost of the system. Some of the calculations that we performed led us to believe that to create a neutrally buoyant accelerometer, we needed to create the overall density of the accelerometer to have the same density as the medium that it's being placed in the array. I'm now going to hand it over to Corey Tupin, who's going to talk about some of the testing and evaluations done during this project.
Thank you, Mark. So over the course of our project, there were there were 4 different testing goals that we had to achieve. Our first goal was to actually test our syntactic foam mixtures that we were making. This involved us testing the density of the foam that we had made, its water absorption, and its hardness. The second test that we did was the actual testing of the accelerometers using this setup right here, which I'll get into in a minute. And this just gave us the sensitivity of what the accelerometers were performing at. And our last two calculations were FEA simulations using console. And this was in order to get the deflection of the cap under the PSI that it's going to be seeing when on the submarine, and also to see how the accelerometers will act theoretically when the internal sensing elements are excited. So now this was the setup that we used in order to physically test our accelerometers. This setup begins with a shaker table here, which has an input frequency that is supplied to it, and the accelerometer is mounted to the top of the shaker table. Now, as the shaker table is excited and it starts to vibrate at a frequency, this displaces the sensory components of the accelerometer. As they're displaced, since they're piezoelectric, they create a voltage. Now, at the same time, there's a photonic sensor which measures the exact physical displacement of the accelerometer on top of the shaker table. Both of these measurements are compiled by this vector signal analyzer here, and we end up with this frequency response plot, which, as you can see from here, the blue line represents the original flat plate design, while the green line represents our curved cap. Now, this plot shows that they're very similar, so the cap didn't have much of an effect at all on the actual sensitivity of the accelerometer. So, as Mark mentioned before, we went from the flat plate design that BTech currently uses to this elliptical cap design. Now, the outside radius is now an ellipse as well as the inside radius. So this made hand machining these caps virtually impossible. So we had to take advantage of the CNC capabilities that are located at the Center for Innovation and Entrepreneurship in Fall River. In order to program the CNC to do these, what we had to do was make use of SolidWorks, and we could take these oblong radii here and break them into smaller triple point arc sections. And then once we had that done, we could determine the radius of each of those triple point arcs. And from there, we could go from our center point located here and get our linear dimensions horizontally and vertically. Knowing the radius and those linear and horizontal dimensions allowed us to program the CNC machine in order to cut these contours to the accurate tolerance that needed to be done. Now, once the caps were designed, we also needed to devise a fixture that would allow us to assemble the caps accurately and repeatably. As you can see here, the base of this fixture holds the bottom cap, and now all of the other components are placed within this top portion one at a time. This portion rides on this rail, keeping them very well aligned, and makes it much easier for accurate repeatable gluing, because technicians will be doing this once they're on a mass scale, so we needed a way to make sure everything was going to come out within tolerance that's needed. This is just a breakdown of the basic components of each accelerometer. As you can see, there's two of our aluminum caps, an aluminum ring, a set of sensing elements that are in a sensing assembly, some wiring, and then here, if you look at the syntactic foam, if we do it the original way that BTech was doing it, we'd have to buy the giant block of foam and then machine it into the smaller components where we would need two caps that are glued together. If we were able to pour the foam though, we would only need one pour over the whole accelerometer in order to encase it. So now, we've mentioned syntactic foam quite a few times throughout this presentation already, but some of you may be wondering what exactly syntactic foam is. If you look at this diagram right here, it's a pretty good representation of the components that make up syntactic foam. It's a mixture of epoxy and glass spacer beads. Now, the epoxy is comprised of a resin base and a hardener, and then there are glass spacer beads that are added to it in order to achieve different density levels. Now, the syntactic foam that BTech currently used was Trelleborg's EcoFloat TG24, which has a density of roughly 0.4, a Shore D hardness of 67.5, and a water absorption of about 2%. So through various trials, which you can see a bucket full of some of the trials that we've gone through, we were able to comprise these two plots here. This plot here on your left shows the density versus the epoxy bead ratio. And you'll notice here on the epoxy to beads ratio portion of the graph that as the ratio increases, meaning more epoxy versus glass spacer beads, the density also increases because the epoxy is more dense than the glass spacer beads. But so our portion of the syntactic foam wanted to be down here below the 2.5 to 3 range, where we're located roughly about 4 to 5 for a density, matching the Trelleborg. And the plot over here on the right shows the density versus water absorption. Now, through the various trials, we went through a few different forms of epoxy and a few different mixture ratios, as you had seen in the previous slide, which some of them were not adequate at all. They had water absorptions of well over 100%, which just for this project wasn't going to work. We needed to be within that 2% range, as I mentioned before. But through all the trial and error, we finally found an epoxy and spacer bead ratio, which put us right about here, where we wanted to be, well below that 2% mark here. I'm now going to pass it over to Greg, who's going to go over some of our testing results for the accelerometers.
Thanks, Wood. All right, so here we have some testing results that we gathered. On the right, there's some console results, and on the left are some actual measured data on our photonic sensor setup that Corey showed earlier. So on your right is a few different variants. It's hard to see, but right here on this black line, it's actually 3 different variants that we've tested. One is their existing flat sensor cap, and 2 different varying radii caps. What we concluded from this was that it doesn't really matter too much the shape of the housing. It doesn't seem to affect the sensitivity too much. So we also included on this plot a actual measured flat cap variant in yellow here, and that was just to verify that our results were fairly close to, from console, or fairly close to the real world. There is some error, but that's just because of the possibly the test setup and also variance in the material used for the sensing elements. It's not always perfect, so it is a little bit lower, but it's fairly close. And then on the left here, we have the curved variant in green, and the blue variant. The blue is the flat variant that they're using existing. This shows that they're very closely related. There is some noise on the curved variant, and that's because the fixture we used for testing was actually optimized. It was designed for the flat caps. We didn't have time to make a curved cap fixture, but it did work, and it does show that the results are very similar. So some of the challenges that we had on this project. The first challenge we had was developing a fixture to actually hold this varied radius cap. You need to machine it in a lathe, but the problem is once you machine the inside, you need to part it off and flip it over to machine that outside radius, but you have nowhere to hold it. And it's very shallow, so it's very difficult to hold it in the lathe. So we had to design a fixture, like a reverse call-out almost, where we could insert it into the inside of the cap, and it matched the radius that the inside of the cap was. And then we could expand it to open up and kind of grab it on that radius. And then we put that inside the lathe. That kind of got rid of that issue. And then the second issue we had was actually finding a proper mixture of epoxy and spacer beads to make the syntactic foam that actually met our density and water absorption. At first, like Corey said, we tried many different epoxies. We were just buying them and trying them out to see what would give us about the right density we wanted. We were able to meet our density pretty easily. The trouble we had was water absorption. So once we met the density, we started trying different epoxies to see where their water absorption was until we found one that gave us about the appropriate water absorption we were looking for at the correct density. Another issue we had was actually reliably aligning the sensor element into the housings. It's going to be assembled by technicians out in the field. They're going to be making thousands of them, so how can we reliably have that done? Everyone's going to do it a little differently if it's not kind of set up for them. So we made the fixture that Corey showed earlier to actually, it's on a rail, so that all the parts come down in the same exact location horizontally, and then you just vertically slide them down and align them, and there'd be epoxy on there, and then they would all just fit together perfectly. And then the last challenge we had was actually developing a cost-effective way to produce these. So the best cost savings we came up with was actually pouring our own foam. It saves you money from purchasing. You have to purchase big blocks of the foam. That's the only way they make it. And then you have to actually have it machined by a machine shop, so it's a lot of time, and that costs a lot of money having a machinist machine it. So our initial budget was $1,000. We spent about $287 of that. That was spent on mostly epoxy for the syntactic foam and some materials for like the caps for the aluminum. We didn't really spend any money on machining because it was at the CIE where BTech's located, and we didn't spend any money on like any 3D printing or anything. They have all those capabilities there. So there's two pie charts here. The one on the left shows the initial housing cost. This doesn't include the sensing elements, but it does include assembly and the components of the housing. So because of purchasing the syntactic foam and having it machined, you can see on the left here, it's about $81 each sensor to have all that done. After we were able to pour our own on the right, you can see that the red portion, which is syntactic foam, is greatly reduced. So now the final housing assembly cost was $63 versus the $81, which was a savings of about $18 per sensor. Just based on the fact that we could pour our own foam. The machining of the caps really costs about the same amount. It's not too much more fixturing or anything. And the other components of it, they're all the same, so none of that changed. So here's a timeline of our project. It was split into 6 gates, and right now we're at gate 6 presentations. So for gate 1, we met with the client, learned about what the project was, what they're looking for deliverables-wise. Gate 2, we started our research. We started looking into how syntactic foam is made. What is syntactic foam? We started looking into different materials that you can use for the housing, caps, plastics, all different sorts of materials. And then gate 3, we began the simulations on console for the caps, varying the radius, trying different amounts of air gaps inside, like amount of air in the sensor, and then making sure the sensitivity wasn't affected by the cap change. Gate 4 was the development stage. So when we started to have the caps machined, we started to make the syntactic foam. We were trying out different epoxy bead ratios. And then gate 5 was the accelerometer testing phase. We started, once we had them fully assembled, we started testing them on the photonic sensor measurement setup, and then we also started testing our syntactic foams, making sure the density, the water absorption, and the hardness was all met. And then gate 6 is just compiling all the data and results that we got and making a document to give to our client. So for future work, in the future we'd like to complete a booklet for the assembly guidelines to make it more reliable. Right now we have some assembly guidelines that we use, but we'd like to kind of get them in a better package. And then we'd also like to create a console model of the entire accelerometer with the foam on it. What we were using in our measurements was without the foam for our console models. It was just on the aluminum housings. This was because we were having trouble getting the actual material properties in console. It's not something you buy on the shelf. Even the ones you can buy on the shelf, they don't give you that data. So we would like to get those material properties somehow and model the entire thing. So in conclusion, we performed the console simulations on the various radii caps. From those console models, we chose the optimal design that we would go for. And then we designed, manufactured, and tested our accelerometers that we made. We also discovered a mixture of syntactic foam that was able to meet both the density and water absorption and the hardness. And we finalized the data for all the results we got for the syntactic foam and the housings to give to our client. And here's some references that we used. And are there any questions?